Hello students, welcome back to PH107 Quantum Physics and Applications. Today I'm going to discuss Schrodinger equation. But before I talk about what is Schrodinger equation and why we need it, let's agree at this point that wave packet is an adequate representation of wave particle duality. It means that if a matter is exhibiting a wave particle duality, for example, light is behaving like a wave as well as like a particles, and the same is applicable to particles like electron, proton, neutrons, which behaves like a particle, but we have seen that they also exhibit like a wave, and this is what we call as wave particle duality. To describe such kind of notion, we needed a wave packet concept, which we have discussed in the previous lectures. And once we have discussed the wave packet concept, we have also learned about the Heisenberg uncertainty principle. Okay, so now today we are going to discuss something along the same line. And before I come to the main topic of the Schrodinger equation, let's see what we know so far. Okay, so let's say in classical world, all the massive objects are allowed to be described as a particle, and once we call them as a particle, we know that the momentum position of these particles are exactly known, which we call as a state of the particle. Okay, now if we know this position momentum of the particle at some time t, and we know that there are some kind of force is acting on this particle, so we can easily deduce the position momentum r, uh, in general state of a particle at some later time t prime, okay, by solving the Newton equation of motion and Newton's second law. Okay, so what is the Newton's second law, which you all know by this time? So this is a second order differential equation with respect to the spatial coordinate, or the first order differential equation with respect to velocity with respect to time. So this is your standard Newton equation of motion or Newton's second law, what you have seen it. Okay, so what it tells you, what it is going to provide us. So let's say if we know the position and velocity of a particle at a given time t, then by solving this equation F is equal to ma, we can easily find out what is the position and velocity of this particle at another time t prime. Okay, and once we can know what are the position of particles at different times t, t prime, and so on, then we can call this as a trajectory of a particle. Okay, so this is what we know in the classical world. Okay, and this is what we call as a dynamical equation of motion or dynamical equation, which governs the evolution of the state of a classical particle. Now let's so when you use this classical picture and think about for example a hydrogen atom, this is something looks like this one. So this is the first impression that you have or had, that this is a nucleus and an electron is revolving around the nucleus, and by using, let's say, the Newton's equation of motion, you can easily find it out, exact its position and momentum of a particle, which we know that is not correct, because there is just something called uncertainty principle, which allows us that we cannot know the position and momentum of a particle with an unprecedented accuracy. Okay, so let's transit from classical to the quantum world. So in this new or quantum world, this picture of exact knowing of the position and velocity or momentum is not valid. So let's ask a question, because let's ask a question that if the particle, if the object is not a particle in Newtonian sense, what it means, then it is also not a wave. Okay, so an object is neither a wave nor a particle, or other way around, a part or an object is behaving like a wave as well as behaving like a particle. So this is what we have called as a wave particle duality. So in fact, there is no answer to what is the object. For example, it is futile to ask what is the electron. Is the web packet the object? No, because it is a function which carries the information about the state of the object, and that too not in a deterministic way but in the probabilistic way. So this new word or the quantum word is not a deterministic but a probabilistic word. And if you want to see how the same hydrogen atom looks like in this probabilistic way, this looks like something like this, which you have seen probably, that this is a nucleus, and now instead of having a discrete orbit you have actually electron cloud. Now you may ask, what is the probability of finding the electron here? Okay, there is some part probability, but at the same time there is also some probability to finding an electron here. So that's why you have a distribution, or let's say the electron cloud picture, which is a probabilistic in nature. So to see this, we first need to revisit the question, what is oscillating in the Debye wave? Okay. In case of classical wave, we know the answer what is oscillating. For example, in the case of electromagnetic wave, the mutually perpendicular electric and magnetic fields are oscillating. In the case of elastic waves in a stretched string, one or two of the spatial coordinates are oscillating. Okay, so we know the answer in the case of the classical waves. Now we have to ask what is oscillating in the quantum waves or in the Debye wave. Okay, so in the Debye wave, the oscillating variable is known as the probability amplitude. So this is the first concept that you are going to learn today. So what is probability amplitude? So let's say this psi xt represents the state of the object. It is the same thing what we have seen in the classical world, that the state of an object is represented by the position or momentum. In the quantum world, the state of the object is represented by this function psi of xt. Now you take the modulus square of this function psi of xt mod square times dx, and this quantity give the probability of finding the particle in between x and x plus dx at time t. Okay, and this is what we call as a probability amplitude, or in other words you could write down, okay, let's take this quantity and integrate over in between a and b. Then what we can say, that the probability of finding the particle between a and b at time t is given by this expression. Okay, so this is known as the Born interpretation or Born statistical interpretation of this state psi of xt, which will be which we will call wave function from here onwards. Okay, and for that Max Born got the Nobel Prize for this interpretation. Okay, so now let's ask, where is the particle? The answer is everywhere. Is the particle at x is equal to x0 now, at t is equal to t0? The answer is yes, but with the probability of psi of x0 t0 mod square. Okay, and that is what is called probabilistic interpretation. So the answer is yes, but what is the probability of finding the particle at this position at this time is given by this quantity. Or in a very strict sense, or in a very correct way, you could say, okay, this is the probability of finding the particle in this integration way, which we have seen in the previous slide. Okay, so okay, let's appreciate that wave function does provide an answer, although in a probabilistic way, about the position, or we could call as a state of a particle. Okay, so now we could ask, what we now need is an equivalent of Newton's second law, what we have seen it, a dynamical equation which governs the evolution of the state of the object. So how your psi of xt changes as a function of time or changes as a function of position, for that we need some kind of equation of motion. The same equation of motion in classical world we have seen is known as a Newton's second law or Newton equation of motion. This is the same thing we need in the quantum world. Okay, so what can this equation be? But before we go into writing down the equation, let's learn more what we know so far. So, of course, this kind of equation is not valid in the quantum world, okay, because this equation does not imply any wave-like solution at all. This is strictly applicable to a particle-like, okay. So now what we know about the wave-like equation, okay. So let's look what is the equation to describe the wave motion. So this is the equation that probably you have seen, which is known as the wave equation, okay. So let's say this is some amplitude of the wave. So you take the double derivative of your amplitude with respect to the position, that is equal to 1 over c square double derivative of your amplitude with respect to the time, and this is known as a wave equation, which governs the equation of motion for a classical wave, okay. Now what are the possible solutions of this wave equation? We could easily check that if we take the following form of this phi of xt in terms of the cosine kx minus omega t with some amplitude a, this will satisfy, this form of phi will satisfy this equation of motion. It means that this is a possible solution. Instead of cosine, if we take a sine function, this will also satisfy this equation of wave motion, okay. Or if we take in terms of the exponential, this will also satisfy. It means that this particular equation of wave motion has several possible solutions, okay. Or this can also be with minus sign, okay. So it means that solutions of this equation must superimpose. So it means that, let's say, if we have phi 1 and phi 2 are the solution of this wave equation, then it means that the linear superposition of phi 1 and phi 2 will also be the solution of this wave equation. So what it means that if I say phi is equal to a times phi 1 plus b times phi 2, this must also satisfy this equation of motion, or this is also a solution of this wave equation, which we can verify very easily. So let's verify it, okay. So this is the equation of motion, d2 phi over dx2, that is your left hand side. Now I'm substituting the value of phi. So what is the value of phi? A times phi 1 plus b times phi 1. I can expand this double differentiation. So a is a constant, so a comes out here. Now I can only apply this one. The same is applicable to the phi 2. What we know that phi 1 and phi 2 are also independent solution of the wave equation, okay. So it means that this part I can write down 1 over c square d2 phi 1 over dt2 plus b times 1 over c square d2 phi 2 over dt2, okay. Now 1 over c square is a common thing, and again a is a constant, so I can again take this a back to here, and I can write down d2 a phi 1. The same I can write down d2 b phi 2, okay. So it means that this is what I have arranged, 1 over c square I have taken out and I have rearranged, and this is what, it's phi. So I can substitute phi. So what I have shown that if my phi 1 and phi 2 are the solutions of this wave equation, then their linear superposition a times phi 1 plus b times phi 2 is also a solution of this wave equation, okay. Note that the new solution has the same velocity, which is the case of the previous condition, okay. So phi would not be a solution of the wave equation if the two waves phi 1 and phi 2 have different velocity instead of c. Then it will be difficult. You can easily verify that in the previous slide what you did, you have taken 1 over c square out. If you cannot do this mathematical step, then it's not possible to show that phi 1 plus phi 2 is also a solution of the wave equation, okay. Now, so this is what all about our wave equation, but let's come back to the wave packet. We know that to form a wave packet, we need waves traveling at different speeds, which need to be superimposed. The dynamical equation should also govern the evolution of the wave packet. So the standard wave equation cannot be used for the Debye waves, okay. So we cannot use Newton's equation of motion to describe the dynamical evolution of the wave packet. We cannot use the standard wave equation, which we have just seen, to describe the wave packet motion. So what we need something different or new equation. Okay, so before we go and discuss about new equation, which we are going to call as a Schrodinger equation, and talk about its derivation, let me make a disclaimer that Erwin Schrodinger guessed this equation. He had not derived from the first principle. So it must be stated that Erwin Schrodinger guessed the form to go the differential equation governing quantum dynamics. Any attempt to derive it is only hand waving. Its success will be judged by its ability to explain observed phenomena. Okay, so let's consider one of the component waves of the wave packet, which is representing a free particle, which is given by this equation. Okay, so psi of xt, now we have agreed that we will call this function as a wave function. So let's, the wave function is written as a free wave e to the power I kx minus omega t, where your k is related to the momentum in this fashion, and this omega is related to energy by this fashion, which you know. Okay, so now let's differentiate this function with respect to time. So what you will get, this will remain unaffected. What you will get I omega times the same function. So I can write down this side. Okay, now let's differentiate the wave function 2 times with respect to x. So you can verify that d2 psi over dx2 will be minus k square times psi, because what you will get, once you will get ix, once differentiation, second differentiation will again give you ix, so you will get I squared k square, and I square is minus 1, so minus k square, and times same the exponential, so you will get back 1. Okay, so this is what we have got when we have differentiated this wave function of the free particle or the plane wave form with respect to time, and this is what we have easy to see that if we multiply this quantity by IH cross in the left hand side, so this we will multiply this quantity by IH cross, so there is minus I square will be I square, 2 times I will be I square, and this I square will give minus, so minus minus 1 will be plus, H cross omega will be E psi. So this is easy to see that this partial differentiation of your wave function with respect to time can be easily related to the energy times wave function. Okay, now this is what we have seen in the case of double differentiation of your wave function with respect to the spatial coordinate. Now what we could do, we can multiply this quantity in the left hand side, and once you multiply this quantity in the right hand side, so minus minus will be plus, h cross k square by 2m, and now this we know what is h cross k square over 2m, then it's easy to say that this is your momentum, so it's a momentum square by 2m, which is equivalent to the energy of a free particle. So this is the energy, and this is the energy of the free particle. So now we can equate both hand side. So this is my E psi, this is my E psi. So now this must be equal to this one. So this is what we have written down, that IH cross d psi over dt is equal to minus h cross square over 2m d2 psi over dx2, and this is what is known as a Schrodinger equation. Okay, which satisfy the wave function of this following form. That's what we have seen it. Okay, note that the equation is free from parameters of the motion of the particle or the associated wave. Okay, now if this wave function or this wave is a wave with infinite extent, but our wave packet is not of infinite extent. Okay, so for the equation to govern the evolution of a quantum physics particle, or let's say the wave packet, which is constructed by using the linear superposition of number of or these plane waves, to satisfy it we need to have a wave packet. So let's consider a wave function in this following form, and this is you have seen in the case of Fourier series that if you have a infinite number of waves, so this summation can be represented as the integral, where this is the amplitude of your wave packet and this is the constituents of your constituents waves of the wave packet. Okay, so this is a wave function corresponding to a wave packet. Okay, so this is the equation that we have seen for a free particle or for one component of the wave packet, which is represented by a plane wave or the free particle Now this is the function for a wave packet. Let's see whether this wave function satisfied this equation of motion or not. Okay, so what I can do, I can substitute this psi first in the this hand side. Okay, so this is what I have done. AK is independent of time, so now this will be independent, only that this will go. So what I will get this I, and here I will get minus I omega k. So I minus I will be minus I square, which will be plus 1. Then h cross is here and omega k comes here, and this is what I have seen. Okay. Now we know that omega is equal to h cross E by h cross, and momentum is your k by this one. Then I can rearrange this particular quantity h cross over omega by using this two term by h cross square k square divided by 2m. Okay. Now this is what is given in the previous slides also, and then it is easy to see that my h cross square over 2m I can take it out, and now k square can be related to this one if you put minus 1 by d2 over dx2 by this function. So you think about, it's a little bit other way around that the mathematical step is done. So suppose this is your function and you have to perform the double derivative of this function, then what you will get? You will get minus k square, because once you will get ik, second time you will again get ik, so then you will get minus k square. So it is equivalent to write that your k square as minus d2 or dx2. This idea comes from your previous slide where we have performed this kind of thing. So then what we have used, we have started with is cross d psi over dt. We have substituted the form of this psi in this following function, and then what we have arrived into this one, which is equivalent to your psi of xt. So again we have shown that for this particular form of your state of a particle or wave function, we do see that this equation is satisfied. Okay, so that's what we have seen. Now we see that the wave packet does satisfy this equation, which we call as a Schrodinger equation. Now what we have to note that this minus IH cross d over dx, what we have seen in the previous slide, d psi over dx, if you apply this thing, what we are going to get? This is the component of your wave packet, and once you apply it, what you are going to get? You are going to get h cross k. Okay, this h cross k, we know what it is, this thing, and this is your psi of xt. So I can write down my psi of xt, and this h cross k I'm going to write down as it is, and now I can write down this psi of xt times this h cross k is your momentum. Okay, so I took this psi of xt as this one. I operated this quantity which we have seen in the previous slide partially, and what we have got by operating this thing, momentum by. Okay, now we can use this another quantity that we have seen. Again we will apply it, we will use it. So what you are going to get? You are going to get I, once you operate it, you are going to get minus I omega, and then you have I h cross, so you have to substitute everything. You will get h cross omega, then I can substitute this as a psi, and this quantity is your E times psi. Okay, now what we are going to do, we are going to now coin some new terminology. And what are these new terminology? So what we have seen, that this quantity and this quantity, when it acts on this psi of xt, it results this, when this psi of xt is representing a free wave, what it gives you? It gives you momentum corresponding to this one and energy corresponding to this one. So then we can call this function as an operator. Okay, and this is called a momentum operator because it is giving the momentum of a particle, and this quantity I can call as a energy operator, and because this is giving you the energy of this function. Okay, now we have seen that now momentum operator can be written as minus is cross d over dx, and energy operator is written as is cross d over dt. These operators are equivalent to your differentiation operation that you have done in calculation. So let's say you have a function, for example sine x, and you want to differentiate with respect to x. So when you perform d over dx sine of x, what you will get? You will get cosine of x. Okay, in that case your left hand side of psi and right hand side of psi is not the same. So here you see, whatever you are operating, at the end of the day you are going to get back the same function. Okay, so this is only true, let's say, when you have a e to the power I or e to the power ikx, or when you have a, let's say, the Gaussian function, then it is easy to define these quantities as an operator. Okay, or I would come into this point. At this point maybe it's not very clear, so let's say, let's agree that at this point of time, when we operate this operator so called on this free particle function, it's giving a momentum, and this operator is giving an energy, so we can call these two quantities as a momentum operator and an energy operator. Okay, so what are the operators? Generally speaking, something that acts on a function and converts it to another function is known as a operator. So as we have seen, momentum and energy operators are the example of the differential operators. Okay, but not all operators are of the differential in nature. So we can call as x some operator which apply or which multiply this wave function, return as small x to give a new wave function. So let's say I can call this phi of xt as x times psi of xt, and when I'm operating this operator capital X, operator always come with the head psi of xt, it will give me x times psi of xt. Okay, so this operator is not of differential in nature, it is form of some kind of multiplicative in nature. Okay, so all the measurable parameters in quantum mechanics are associated with some operators with special property. Okay, so here is the first quiz for you. In classical world, we have seen that momentum is a real quantity, mass time velocity. Okay, it is associated with the velocity of a particle. But what we have just seen in the quantum world, that momentum is an imaginary in nature. Our momentum operator is in imaginary in nature. It's minus is cross d over dx. Why it is so? Think about it and answer it. Okay. So this is the Schrodinger equation, what we have seen it. Now we have learned the operator. So is cross d over dt is the energy operator. So let me write down as energy. Let me take 1 over 2m out, and this minus h cross square I can write down as minus is cross d over dx, minus is cross d over dx, d2 over dx2 is written 2 times d over dx. This I know what is this operator. This is my momentum operator. This is my momentum operator. So now I can write down p hat square over 2m. So this is my Schrodinger equation in operator form. Okay. Note that here the particle is not subjected to any external force because it is a free particle. So there is no potential term which corresponds to any kind of external force. Okay. So let's talk about what happens when particle is in presence of some force or particle is under force. Okay. In that case, your energy is not related to only the momentum, but it has to have some potential term V. Okay, so it means that total energy is a sum up to kinetic energy plus potential energy. This is what you have seen, for example, in the case of harmonic oscillator. The total energy of a classical harmonic oscillator is a sum of the kinetic energy and potential energy. Okay, so now this is what we have seen in the previous slide. So what we could do easily, that this concept, by using this energy one, we could easily replace by an operator corresponding to the potential. Here we don't know what is the form of the potential. We are trying to write a very general form. So this is the operator form of a Schrodinger equation of a particle which is under some kind of force, or this is in the presence of some potential. Particle is experiencing some kind of potential. Okay, so this is what we have seen. This is in a differentiation form of the Schrodinger equation with some kind of potential, and this is what we now call as a time dependent Schrodinger equation, or we will use time to time an abbreviation TDSE. Okay, and note that here only one coordinate of your spatial variable is involved, so this is what we can call as a one-dimensional time dependent Schrodinger equation. In 3 dimension, we can replace by d2 over dx2 by d2 over dx2 plus d2 over dy2 plus d2 over dz2. So this will be your this operator, Laplacian operator. Okay, so this is the Schrodinger equation for a particle in 3 dimensions in the presence of some external force or in the presence of some potential. Okay. Now, what are the possible values of the wave functions? So far, we have talked about the operators. Now, what are the possible values of the wave function, or what form of the psi is acceptable and what form of the psi is unacceptable? Let's discuss this in detail. Okay. So, what are the restrictions on the nature of psi of xt? So, we have discussed in the last slide that this is the probability of finding the particle between A and B at time t. Okay. This implies that if you go to entire space, the probability is supposed to be preserved. You know the probability is always 1. So if you add all these probabilities between different intervals, it has to be summed up as 1. Okay. So this is the first restriction, that whatever form of the wave function you are choosing, it has to satisfy this condition. Okay. This is what we have talked about. So in 3D, you could write down, instead of x, you can say, okay, now I have r variable, and this has to be, again, it has to fulfill this condition, where this d3r is the volume element in the Cartesian coordinate. It can be written as dx, dy, dz, r in spherical polar coordinate, which you will see maybe in this course or maybe in the next course, can be written as r square sine theta dr d theta d phi. You don't need to worry too much about this one. Okay, so let's ask a question: what kind of wave function are acceptable? Okay, so wave function need to be single valued at all x. Okay, so this form of the wave function is single valued at all x, not single valued, because you can see this. Okay, the wave function and its first derivative, both with respect to x and t, must be continuous at all x. Okay. So this function is not a continuous at all, so not continuous, and this function's derivative is not continuous, so this function is also not acceptable. Okay. Now, what it's called as, we have seen that the probability is supposed to be preserved. So suppose wave function must be square integrable. So if you perform the integral of this quantity, it has to give a finite number. It's supposed not to be an infinite number. So for example, this wave function is also not acceptable because this function is not square integrable. Okay. So let's talk about square integrability or normalization of the wave function. So let's say psi of rt is a solution of TDSE of this one. It means that if I multiply some constant a to this wave function this wave function psi, then it will give me another function which I represent as a phi, which will also be a solution of this equation. Okay. Now there is another concept. Since the modulus square of the wave function is a probability distribution function, it means that this must preserve this as 1. Okay, this is always employed. So whatever function which satisfies this equation, that also must satisfy this square integrability, or what you say, that the wave function must be normalized. It means that if you take the modulus square of this function and integrate over entire space, it must be equal to 1. Okay, so this condition fixes the value of a process known as normalization of the wave function. So let's look an example. So let's say this is my wave function given with some constant a, and this is wave function. Now let's, a is some positive real quantity we don't need to bother about. So let's check what is the value of this a, so such that this wave function is normalizable. Okay, it means that this wave function must satisfy this quantity. So I can substitute this form, and you know that when you have modulus square, so it means that psi times psi star means that it's complex conjugate, so the I will replace by minus I. Okay, so this plus I and minus I will cancel out. A will be a square, and here you have a e to the power minus a mx square over h cross, and here you have the same, so you will have 2a times mx square over h cross square. Okay, the t part is cancelled out, and we know the value of this integral using our knowledge from the previous lectures. This is a Gaussian function, and we know the integral of this Gaussian function. which is in this one. So A is equal to 1 over this quantity and square root of power 4. So the psi of xt is this quantity. Okay. So this is what we have done, that how to normalize a given wave function and find a normalization constant A. Okay. So let's consider another example. So this is a wave function for a free particle or free wave, which we have seen it, and we will see in coming lectures more about it. Okay. So let's check whether this wave function is normalizable and what is the possible value of A. Okay. So it is easy to see that when you substitute this value, this e to the power minus I and e to the power plus I will cancel it out, and there will be no function which will depend on either x or in t. So you are left with only mod of a squared d over dx, and this quantity is not going to give you any meaningful value. So it means that this wave function is not normalizable. Okay, or then we can call it this wave function is not square integrable. So it means that this wave function is not going to represent a state of a real particle. Okay, so before I end today's lecture, let me provide the recommended reading. So if you would like to read more about Schrodinger equations and related concept, please go to sections 6.1, 6.2 and 6.3 in this book by Survey and co-authors. Thank you very much and see you in the next class.